Hi there, it's Wolfgang again. Today I'd like to talk about a mostly ignored but very important issue when flying any type of remote piloted aircraft like planes, helicopters or drones. Before GPS stabilized model aircraft were commonly available, a hobby pilot had to train a lot on a simulator before even thinking about flying the real model, because without proper training it wouldn't survive its maiden flight in most cases. Flight simulators were very popular then. These made it easy to train your reflexes on flight maneuvers without risking a damage to your model. I used the flight simulator a lot when I started flying model helicopters, like this bad one here. And it really helps on one thing: knowing your aircraft's attitude. To avoid crashes, a pilot is supposed to know the orientation of the aircraft at all times. Only this knowledge gives a pilot the opportunity to correct for wind drift, steering the aircraft in visible line of sight, and successfully avoiding obstacles on the flight path in time. Nowadays, remote aircraft, especially drones, which are very popular now, can hover on the spot automatically without any intervention of the pilot. That's of course a very handy feature, and this made drone flying so popular, I think. So now everybody can fly a drone without risking much, but it is a false sense of proficiency and safety. How is the pilot drone system working? Well, it's a kind of a control loop. Let's say the aircraft travels nicely along. The pilot's eyes see that, and his wetware processing unit called brain processes that information, which may use, say, 0.3 to 2 seconds. The brain sends nerve impulses to the pilot's hands to move the sticks for a correction, which the brain thinks is about correct. The pilot doesn't know yet because he hasn't issued the correction. The fingers now start to move the sticks, which in turn is transmitted to the aircraft, which in turn reacts to it. Let's assume this takes another 0.3 seconds. Only a few seconds later we see if the correction was sufficient and if more correction is needed or not. Every single step of this takes time. Let's call it round-trip loop time. In our case it's about 4 to 6 seconds. Everybody who is into control loop technology knows that big time delays in a control loop is a very bad thing. It makes the system unstable and sometimes totally unpredictable. I remember 2006, some 30 years ago now, when I designed my very first quadrocopter, which wasn't possible to buy them or even parts back then. It had no gyro sensors to regulate its attitude itself. I found out very quickly that this is totally impossible to fly. I crashed it every time no later than 5 seconds after takeoff. That was because of our round-trip loop time. Using a gyro-based control loop did solve the problem nicely, because simple electronics can work very fast with a very small delay time. My brain was simply too slow in reacting properly to attitude changes. Let's have a look how modern GPS stabilized drones work. You can see them as having 4 levels of control loops. First and most basic level, regulate the aircraft's attitude so it can fly smoothly without wobbling around. This is done inside the drone electronics with gyros and sometimes accelerometer sensors. These sensors can output values more than 1,000 times a second, very fast. Second level, regulate the aircraft height. This is also done inside the drone electronics with a barometric sensor to sense the air pressure, which is a direct function of the height. Usual barometric sensors can output values some 50 times a second. That's not very fast, but it's not that critical since an aircraft has a takeoff mass which prevents it to jump around too fast. Sometimes accelerometer sensors are used to assist the barometric sensor. Some drones even have laser sensors, vision or camera-based sensors, to increase accuracy here. Third level, regulate the aircraft's position over ground. That is done with GPS-based systems plus a compass sensor. Modern systems can output GPS fixes 10 times a second. That's quite slow, but again, there's also a lateral inertia involved, which helps. Plus, one needs to know that the GPS fixes are not exact. Depending on the amount of satellites and their signal reception quality, GPS-based systems have a positional accuracy of 2 to 5 meters. Last but not least, fourth level, the pilot. Compared to the aircraft systems, our reaction time can be a whole second or so, at least if you omitted the pre-flight beer, forget about it. We need to take into account that our brain reacts to impulses in a manner that's based on previous experience. We like to repeat things that did work out in the past, but have problems to adapt quickly when we surprisingly face a totally new problem. In that case, we need several seconds to make a decision and execute it. That second can be quite a bit faster if we train it, the experience thing. Let's have a look at the flight log of a typical DJI Spark flyaway. We see that the aircraft dropped to ATTI mode surprisingly due to a still unfixed problem in DJI's IMUs at 3 minutes and 25 seconds. One of the aforementioned control loops had passed away. The pilot was totally surprised. I assume that he, as a responsible pilot, still watched his drone flying away. His drone was about 300 meters away from the home point at that time. Now let's see how long it took before he decided to do something about it. It's a whopping 7 seconds. It seems the pilot had no idea which direction the aircraft's nose pointed to, where the home point is in the drone's perspective, and what direction the wind was blowing. Assuming all this, I can't really blame the pilot here. He was caught by surprise and did what he thought was the best. He climbed the Spark even further, while he was already flying more than 200 meters high. Now I'm getting to the point of this video. Know your attitude, always, even when flying GPS assisting boring tripod mode. Because something bad can happen in flight time anytime right now. It is so important, especially when you don't fly nearby, where you directly see the orientation of your bird. I advise you to have a look at the guys doing drone racing. Their drones don't use GPS, since they do fly indoors most of the time anyway. Nobody can do conscious reactions that fast, but subconscious reactions can do that. These folks study the course thoroughly beforehand. They know how fast they are and what radius is needed for a turn at a speed. They train for many hours every day to perform that well. It's simply impressive, and I'm sure it's a lot of fun. I admit I've never tried this. I'm too cowardly about that. Everybody who has flown a small bird like the Spark or a Mavic some 200 meters away knows you simply can't judge the orientation of it. Yes, you see the aircraft, but you see only a dot in the air, that's it. The only thing you can do about it is knowing the aircraft's orientation, its attitude at all times during the flight. Let's say you want to fly a large circle. You put in a bit of nick to accelerate, a bit of roll to bank it, and then add yaw to make a nice coordinated turn. If you know that you are flying a circle that way, you won't have a problem if the bird drops to ATTI mode in the middle of the circle, and you'll instantly know what to steer to pilot your bird home safely. That's the whole point of my video about enabling the ATTI mode on the Spark. See the description below to find that video. We need to train this seriously to be better and safer pilots. And by the way, it also saves us money, which is a good thing, right? I'd like to say a word pro flight simulators. If you have the opportunity, you may know a buddy or someone who has a flight simulator. Please try it, it's worth the time. Even freeware simulators are good enough to train this. because judging the orientation with only 2D sight is especially difficult, more difficult than in reality. Which is a good thing, since we want to train for the worst case, right? Yeah, of course, the cheap simulators or even free simulators don't look so great, but that's not the point here. Unfortunately, DJI does not give us the possibility to use the Spark's remote controller on a PC. Only for the more advanced remote controller models these are available. Maybe you are able to borrow an old school remote from a friend for some time to do the simulator training. Or you can buy a cheap used 4-channel remote on eBay. There are plenty of them because people switch to modern 2.4 GHz remotes, dumping the old 27, 35 or even 40 MHz remotes. These old remotes often have a connector that outputs a PPM signal, which can be connected to a PC or laptop via an interface. Okay, so that's it for today. If you like this video, please give it a big thumbs up, as this always helps. Fly safe and bye bye.